Hello, everyone. My name is Nick Painter. I'd like to welcome you all today to the webinar that we're hosting. It's going to be the Underground Design Conformance 101 webinar. Our presenter today is Laird Horrigan. He's a licensed professional engineer here in Colorado. Laird's a mining engineer by trade, and he works with the Maptek technical services team, and he performs client training. He does some technical consulting, and he also contributes to the development in the North American region. So Laird's worked in the industry for nearly about 10 years as a consultant, and he's also a member of our team here in North America. Without further ado, I will hand over to my very sharp-witted colleague, Laird. Please take it away.
Thanks, Nick. My name is Laird Horrigan, and I'm a member of our technical services team here at Maptek. I support the software through technical support, consulting, product testing and development, and of course, training. Before we get started here today, I'd like to take a moment for safety share. A perspective that I often find myself in is when visiting a site, or for those in operations, if you're working in an area that you don't frequent, some things might stand out as concerning or might not look right. It's often the case that this opinion is not shared with the group, but it is an important one, and thinking about these safety concerns from a new lens can be very helpful for addressing hazards and potentially considering things that might go missed otherwise. Thanks for joining today as we discuss design conformance as it relates to safety, cost, and production. Before we get started here today, let's take a brief poll to discuss or consider how design conformance is viewed at your site. The question being, at my operation, we monitor design conformance for every excavation, both production and waste, only in ore production areas, in areas we're concerned about stability, or if we actually don't monitor design conformance. Take a couple seconds, review the poll, and then we'll discuss the answers. All right, the results are in. It looks like the majority of folks are leaning towards design conformance for every excavation or in production areas. This is great to hear. Let's move over to the agenda for today. Today we'll discuss safety from an immediate and a long-term perspective. We'll discuss costs, both upfront and hidden. We'll take a look at design conformance as it relates to recovery, dilution, and equipment operation. Finally, we'll consider a case study. When considering safety, immediate stability and ground support concerns must be addressed. In the image on the right, you can see the designed drift in this case, outlined in gray, the surveyed scan collected here and colored with a spectrum indicating distance from design, and a red line indicating what might be a geotechnical feature, a fault, or simply a delineation between different rock types. The original design was intended to minimize, if the area on the left is less stable, exposure to this unstable area. You can see the as-built extends quite a bit in terms of overbreak into this potentially unstable zone. This opens up some unintended risks as the original design and perhaps the orientation of the drift was more stable as planned. In this area, looking at it from a cross-section, we've extended overbreak on the left rib more significantly than on the right. This might require us to add a few more bolts to the pattern, or if the rock really is unstable, have to consider additional ground support measures such as rock mesh or, as seen in the image on the right, straps. This might be something that we can address relatively fluidly through operations, but perhaps it considers further evaluation from engineering or the geotechnical team. Other immediate safety concerns relate to intersecting with historical workings. In this example on the right, you can see the design drift outlined in a similar gray color and the scan or picked up as-built colored with a similar spectrum. The issue on the right-hand side is that the as-built has deviated significantly from the design as intended. An exploration borehole is simulated here with the blue line, indicating that we've opened ourselves up to an unintended risk. If perhaps this borehole is now bearing water after it was drilled many years ago, there could be risk for inundation in the drift, or perhaps if poisonous gases are present, evacuation might be required. In this example, we don't have a choice and we must address these safety concerns right away. Similarly, moving forward, if we don't document our excavations properly, we can open ourselves up to risks of encountering these later in the mine operation. By documenting them up front, we also collect an important baseline for any future stability concerns in terms of convergence in a drift. Without this baseline, we're only able to compare once we actually recognize that there's an issue present. Let's move into cost. What is the cost of poor design conformance? We'll cover some upfront and hidden costs today. Upfront costs are usually incurred immediately, and they're more obvious. These are the costs that often get focused on. Some of the hidden costs might be more difficult to quantify, and often are realized later in the development cycle. In the case study today, we'll find that these hidden costs might, in many cases, be more significant than some of the upfront costs. Upfront costs. We'll realize these typically during operations. In the images or the screenshots on the right, you can see the as-built is indicated with a pink line, whereas the design is a faint gray line. Overbreak seems to be an issue with nearly every one of these sections. You can see in the back, we've extended beyond our design quite a bit, and in section FF, we've deviated to the right quite a bit. The immediate thing we'll notice here is that we must handle more material. We'll require more mucking trips, extending the development cycle quite considerably. This extra material will not only come at a cost of additional cycles, but also labor or contractor costs, depending on your operation. In the example of section FF over here, you can see this drift has increased in dimension quite a bit, so we'll have to add ground support. Not only will the cost of additional bolts be considered, but labor and more equipment will be tied up, shoring up this drift. Looking at the sill, you can see that there's generally pretty good design conformance. However, what is difficult to tell with these sections is whether or not we have undulating or changing gradient along the drift. If we create areas or low spots, there may be pumping requirements or simply developing drainage controls so that the drift can remain passable. The last cost that's immediate, and hopefully no one ever encounters, is a cost associated with resolving an immediate safety concern. Referring back to the borehole example from before, we don't have a choice when to correct these issues. They must be addressed as we incur them. These can be quite significant and can slow production or development activities to a halt, adding further costs. Moving over to hidden costs. The assumption here with hidden costs is that the baseline scan, survey, or as-built must be collected. Without collecting this information, these hidden costs will go unrealized. With this information, we can then determine some of the hidden costs. One example might be excessive explosive consumption. In areas of this drift on the right, you can see the areas of red, orange, and yellow deviate from the design, as we've seen with similar color shading before. Clearly, we've used too much explosive for either this rock type or it was drilled in such a way that we've overbroken beyond the planned design. How might we be able to resolve this? Perhaps we need to modify our blast pattern. Perhaps we need to look at a different explosive. Or perhaps our perimeter control just needs to be a little bit tighter. With rough areas of the drift, as seen here, we might also find implications to our ventilation. In this example, we really only have two areas of considerable concern. But along a longer development drift, or if this is a repeated problem, we could create much more resistance than originally designed or planned for in our ventilation model. To resolve this, we might have to change our fan operating point, we might have to install additional ventilation controls, or it might simply slow down our development cycle, having to wait longer after blast for the air to clear. Equipment damage and excessive wear can add up over time, and if we are unable to maintain proper designs through overbraking or inconsistent gradients, we might find that equipment wears out, requires maintenance more frequently, or simply has to be repaired more often than planned. This can be as simple as having to repair flat tires every now and then, which might not seem like a large cost at the time, but with consistent issues and repeated flat tires, these costs can really add up. The last cost associated with hidden cost has to do with loss and dilution. We'll consider this in our case study to follow. Now let's move on to the impacts during production. How does poor design conformance hurt us operationally? In the image over on the right, you can see a long hole stope with the CMS scan or as-built outlined in red and the design or the plan outlined by the triangulation in gray here. Ore loss and dilution impact our resource recovery and our downstream processing quite considerably. Other issues with overbreak is with a primary and secondary stope configuration. If we overbreak both of the primary stopes, we might have to modify our plan, resizing pillars or redesigning our secondary stopes to ensure proper stability in the area. With backfill, with overbreak being considerable, depending on our backfill type, either being cemented or paste type backfill, there can also be costs associated with these larger voids. Equipment inefficiencies also can hurt us with design conformance. We're unable to maintain grades. Perhaps we exceed the gradient for the equipment or recommended operating gradients, and the equipment must slow down more, downshift, and apply the brakes. These can be both costly from a maintenance standpoint, but also from a time perspective, adding precious seconds to the development cycle. Similarly, with tight curves, the operators must slow down, as seen down in the bottom here, with this LHD entering the stope. The image on the top, you can see a truck is being loaded, but there's ventilation controls and possibly a little bit lower back than anticipated. This might impact our ability to fully fill the truck to its capacity, and the operator might just need to slow down a little bit more. These can really add up as we repeat the development cycle over and over again. Let's take a look here at the case study. We'll use the same long hole stope that we've seen previously. We'll quantify dilution, loss, and apply some downstream costs. The image on the top left highlights the areas of overbreak, indicating that the areas in red are more significant than the areas in green. The design stope is highlighted in gray. Down in the bottom image, the underbreak is represented in areas of blue, with more significant areas of underbreak highlighted in pink. In this case study, we'll report and quantify the different tonnages, we'll apply some assumptions, and then compare the bottom line. The first step for this comparison is to understand what the targeted design quantities were. In this case, the stope design was 290,000 tons. The CMS scan, or the actual design, the actual excavation, mined 350,000 tons. It's quite a bit of overbreak in this scenario. The important tonnage to understand is the common tonnage, or how much of the design or plan did we actually target. In this case, it's 275,000 tons. The difference between the common tonnage and the stope design represents the underbreak, or in a production environment, we might refer to this as a loss. This loss is 15,000 tons for this example. And moving further, overbreak is quantified at 70,000 tons. This is the difference between the actual or the CMS scan and the common tonnage. In this example, a different density was used for waste and ore, so these numbers won't add up exactly. Contained in the underbreak, or the loss, is lost ore in terms of gold. Here, about 12,000 grams have been lost. And applying basic assumptions for recovery, cost, and selling price, we've assigned a value to this gold. Here, a loss of about $500,000 is contained in this 15,000 tons. The overbreak mining cost was broken out separately from the cost of processing this material as dilution. This can be an additional cost that's not highlighted here, but as you can see, simply mining and hauling this material for dilution adds an additional $1.1 million. These two costs, through lost revenue and additional costs from mining dilution, add up to about 1.6 million dollars. Our goal by practicing and understanding this design conformance would be to improve our excavations and bring both of these numbers closer to zero. You might ask, what are some solutions? How can we understand and report these different quantities? On this slide, there's a few examples. The first being a grid that breaks down the different categories in terms of distance from design, assigns some basic density parameters to calculate tonnages. This image corresponds to the image on the bottom left. The areas in red indicate 2 meters or less deviation from the design. Another option is to look at a development drift sectionally. Here, the requirements are a center line, the design, the CMS scanner as built, and a section interval frequency in order to understand or analyze the individual sections. Here, underbreak is represented in blue and overbreak is represented in red. With this sectional analysis, we're able to understand that the deviation is about 22% for section 5. Now let's take our second poll. If you measure, quantify, and report design conformance, who do you share the reports with? Others in engineering, operations, management, only those that ask, or all of the above? All right, it looks like for those that are practicing design conformance monitoring on site, the information is getting disseminated pretty much with all of the options. That's good to hear. So in summary, design conformance can only be understood if we collect the scan information as a baseline. This must be surveyed either with a drone, we can use LiDAR or laser scanners. The information is becoming more and more available at a lower cost. Without this information, we're really unable to quantify overbreak and underbreak or loss and dilution in a production area. By quantifying the overbreak and underbreak, we can highlight safety concerns, we can calculate costs, and this allows us to uncover hidden costs of ore loss and dilution in a production area. The important step here that it sounds like most participants are following along with are reporting the findings with all stakeholders. By doing this, we can take the information to hopefully improve operational results moving forward. Without reporting this information, it's difficult to make much of an impact on site. You'll see the image to the right here is generated with a sectional-based system or analysis with the distance along center line to determine when the sections should be calculated. Here, with just the 3 inputs of the center line, the as-built, and the design, we're able to generate quite a bit of information and present it in a very logical or meaningful way. Similarly with the blue for underbreak and the red for overbreak, and a deviation percentage on each section, this information can be quite impactful. And that's all I have for today, so I'll flip it back over to Nick and we'll take some questions.
Thank you, Led. Appreciate that. Very insightful. Just while we're on this slide, just some of the contact information. If you have any questions you'd like to reach out directly to Led, please feel free to do so. Led, if you're ready, let's hit some questions.
Yeah, fire away.
Cool. So the first one I've got here is, what software do you use to compare the designs to the as-built excavations?
Sure. I guess it shouldn't come as too much of a surprise, but um, typically when doing this, I'll either use Vulkan, the survey module there, or in Point Studio, we have the ability to take the scan, process it, and compare it to the design all in one package.
Awesome. And then a follow-up question to that is, how time consuming is it to generate these types of reports, Led?
In Point Studio, I guess depends on if you're bringing the information or the scan data in and processing it, or if you're receiving that from survey and processing this after they've, kind of worked with the point cloud. But with, as mentioned, with the triangulation or the solid for the design, the as-built and a center line, these reports might take 15 or 20 minutes to generate. On the Vulkan side, I'd say with those same inputs, the sectional based method, you're able to generate these outputs in maybe 5 minutes.
Awesome, thanks. Then I've got a question here as well, that some of your comments on the ventilation impacts were missed. Could you just reiterate what those impacts are, Led?
Sure. So if we have a continual issue with overbreak, adding, that rough surface to our drifts, or having to add additional, rock bolts, mesh, steel sets, or anything, are just going to increase the resistance in the drift that potentially wouldn't be planned for or designed in the ventilation model. This might be as simple as having to adjust the fan operating point. Of course, that would come with a cost if we are running the fan, consuming more electricity, or perhaps we need to install more bag line or anything to get fresh air to the face. If we're finding that, by not maintaining that smoother surface, or, not practicing a good perimeter control, that can really add up over the course of, 100,000, 2,000 meters or feet, depending on where you're working.
Awesome. Then just a question here on how you colored your stopes here. How did you color the overbreak and underbreak values? Were those colors done by volume or by area?
Those are by distance. So I'm not sure with the coding and the technical nature, but it's going to compare a distance based on the facets, a perpendicular distance from the triangulation facets. So I can't necessarily pause this animation, but you'll see on the corner here, this area deviates quite a bit. And when we can look kind of right there on section, that area is thickest and compared to the design. So it's by distance, I guess, is the easiest way to say it.
Thank you for that, Led. Then what data is required to get meaningful results?
Sure. If we're doing a sectional based analysis, we could survey a few points at a regular interval. However, with that limited data, that limited input, we're only going to be able to compare the points we measure. So with the addition of a drone with photogrammetry data, or perhaps a laser scanner, we're able to collect really dense data to compare against our designs. You can see here with the wireframe, the data has been processed and filtered so that we're not, spending hours running these models. It's able to calculate the values and the differences pretty quickly. So hopefully that answers your question.
I think it does, and it's a great segue into the next question, where I'm guessing if you don't have any of those technologies in your mind, using rough assumptions, do you think it's even worth doing that?
Yeah, I think so. I think one takeaway here is, being on the engineering side of things, tonnages, volumes, quantities, grades, that all means something to us because we're talking those terms every day. But even with rough assumptions for recovery, cost, selling price, putting a dollar figure on, overbreak, loss, dilution, whatever the case may be, that really can send the message to those in management, others in the operation, that really lands the point. And yeah, if the numbers work out, you can very easily make the case for purchasing a scanner or something like that.
No, absolutely. And then I think I'll end this session because we're coming up to time on the last question, which is a bit of a bombshell. What's one of the best ways to mitigate overbreak in development headings?
Oh boy. Well, I think that a lot of it comes down to blasting, but without good drilling going into it, we're not really setting ourselves up for success. So I think the biggest thing that I've seen is perimeter control. Having the right pattern, the right sized holes, the right timing or delays to really maintain those clean faces. And also, if we're rushing our drilling, we'll tend to find deviation in the drill holes, especially with a long hole stope, there's a lot more opportunity to deviate. So there's definitely a balance with how quickly we need to go to, maintain profitability, but also understanding that if we rush it too much, we can deviate beyond the design, which, as shown here, can be quite costly as well.
Absolutely. Well, thank you very much, Led. On behalf of the entire Maptek team, we'd like to thank you for attending today, and we hope you have a great rest of the week. Thank you, everyone.